In this video, we're going to look at another application of logistic growth. Assume that the population of salmon in a fish farm follows the logistic growth model. dp/dt is equal to Kp times 1 minus P over M. At t equals 0, the fish farm is populated with 100 fish. When the fish population is 500, the rate of growth of the population is 200 fish per year. Assume that the total carrying capacity of the fish farm is 1,000 fish. After how many years does the fish population reach 800? So we're going to assume the logistic model dp/dt is equal to Kp times 1 minus P over M. The initial population, P of 0, is 100 fish, and carrying capacity is 1,000. That's as much fish as this fish farm can support. So we're also given dp/dt, the rate of growth of the fish in the salmon farm, to be 200 fish per year. And this rate of growth is when the population is 500 fish. All right, so let's apply the logistic differential equation to solve for k. So we have dp/dt is equal to Kp times 1 minus P over M. Now dp/dt is the rate of growth of the fish, that's 200 fish per year, is equal to K, and the population is 500 at that point in time, times 1 minus P, which is 500, divided by the carrying capacity, which is 1,000, divided by M. Now let's solve for K, and we get 200 is equal to K times 500 times, this is just a half, so 1 minus 1/2 is 1/2. So we have 200 is equal to 250K. And solving for K, we get K is equal to 200 divided by 250, and K comes out to 0.8. All right, so we can rewrite the differential equation, dp/dt is equal to K, which is 0.8, times P, population, times 1 minus P divided by M, which is 1,000. P of 0 is equal to 100. So we now have an initial value problem. We have a differential equation, and we have the initial population, initial condition, and we're able to solve this through separation of variables. But we don't have to do separation of variables, because in a previous lesson, we actually derived the explicit solution to this differential equation. So what we have is dp/dt is equal to Kp times 1 minus P over M, and initial condition, P of 0, that's the initial population of the fish, is P0. And we solved this, and we found an explicit solution for the population as a function of time, is equal to capital M, divided by 1 plus A, e to the minus kt, where the constant A is equal to capital M minus P naught divided by P0. So let's substitute these quantities in. Capital M, the carrying capacity of the population, is 1,000. The initial population of the fish farm is 100 fish. We computed the constant K. K is equal to 0.8. And we can solve for A. A is equal to capital M minus P naught divided by P naught. So we get 1,000 minus 100 divided by 100. And that comes out to A equals 9. So let's substitute these quantities in and get an explicit function for population as a function of time. P of t is equal to 1,000, that's M, divided by 1 plus A, which we found to be 9, e to the minus kt, and k is minus 0.8, so minus 0.8 t. All right, so now we want to find the time in years such that the population rises to 800 fish. How long does it take for the population of the fish in this fish farm to become 800? So this is a simple solving part. So P of t is equal to 1,000 divided by 1 plus 9 e to the minus 0.8t. P of t is equal to 800, solve for t. So we get 800 is equal to 1000 divided by 1 plus 9 e to the minus 0.8t. So now to solve this, let's divide 1000 divided by 800. So 1000 divided by 800 is equal to 1 plus 9. You can also cross multiply and solve it that way, any way that works. So 1000 divided by 800, that simplifies to 5 over 4. On the right hand side, we have 1 plus 9 e to the power minus 0.8t. Let's isolate the exponentials. So we have 5 quarter minus 1, and we get 1 quarter is equal to 9 e to the minus 0.8t. Now divide by 9 both sides, and on the left-hand side we get 1 over 36, the 9 cancels. On the right-hand side we get e to the negative 0.8t. So now let's log both sides so we can solve for t. So logging both sides, we get log of 1 over 36 is equal to log of e to the minus 0.8t. So we get log of 1 over 36, and log cancels e, and we get minus 0.8t. Solving for t, we get t is equal to log of 1 over 36 divided by negative 0.8. Now, if we apply the log rules, on the numerator, we get log 1 minus log 36. That's one of the log rules. If you have log of, say, log of a over b, this is equal to log a minus log b. So on the denominator, we have minus 0.8, and log of 1, of course, is 0. So we get minus log of 36 divided by minus 0.8. The minuses cancel out, and if we decimalize this, we get approximately 4.48 years. So that means that it will take approximately 4.48 years for the fish population to reach 800. Now let's do a little bit of basic skills review, because you're going to need these when you do questions like this. So log of 1 is equal to 0. Log of e is equal to 1. E to the ln x is equal to x, because e to the x and log x are inverse functions, they cancel out. And also log of e to the x is equal to x. Log of x over y, if you divide, you subtract. That's the way to memorize it. So we get log x minus log y. And if you have a product, you add log of xy is equal to log x plus log y. Log of x to the r is equal to r log x. And don't forget the exponential law, e to the x plus y is equal to e to the x times e to the y. And of course, e to the 0 is equal to 1. That was just some basic skills review. All right, thanks.